Hello everyone, welcome back. Today I'm going to be changing it up a little bit and doing the problem of the day on Leetcode. So if you're struggling with that at all, hopefully this video solution will help. This one is a Leetcode easy. It's probably a harder Leetcode easy in my estimation, but let's just jump right into it. I plan on doing the Leetcode problem of the day on this channel for the foreseeable future. The only issues might come up if I'm not home and I can't get to my setup and actually record the solution to the problem. Then it might take a couple days for me to get back to it and record a solution. So in this problem, you're given an array of integers stones where stone's I is the weight of the ith stone. So pretty straightforward. So we have in this example, weight 2, weight 7, weight 4, weight 1, weight 8, and weight 1 stone. We are playing a game with the stones. On each turn, we choose the heaviest two stones and smash them together. Suppose the heaviest two stones have weights x and y, with x less than or equal to y. The result of this smash is if x equals y, then both stones are destroyed. And if x is not equal to y, the stone of weight x is destroyed, and the stone of weight y has new weight y minus x. At the end of the game, there's at most one stone left. Return the weight of the last remaining stone. If there are no stones left, return 0. In this case, we can kind of step through what they say here. We start off with 8, 7, 2, 4, 1, 1. So you take 8 and 7, smash them together. Since they are not equal, we now make the weight the larger one minus the smaller of the two. So we get a weight of 1. So 2, 4, 1, 1, 1. We now take 2 and 4, the two largest, smash them together. We get a new stone of weight 4 minus 2, since 4 and 2 are not equal. So 2 is our new stone. We then take 2 and 1 from this, smash them together. They're not equal, so now we get a new stone of 2 minus 1, which is 1. And I'll take the two largest here, 1 and 1. They're equal. We smash them, so we're left with just one stone, which is 1. So we would return 1. And then in this case, we just have one stone. So obviously we're already at the end condition. So we can see here the stone's length is not that long, which actually might be why it's considered an easy. You can actually kind of see a hint of the way that I want to solve this, especially if it was a larger array. We'll get rid of this for now. But essentially the first solution that we could do is simply, there's kind of two n squared approaches that I'm thinking of here. The first one is to just iterate through the array and find the maximum, take it out. Or I guess what you can do is to have a quicker deletion, you can swap it with the last element because the order doesn't really matter, and then delete that last element. And then do the same for the next stone. Oh, first of all, we're doing this all while len of stones is greater than or equal to 2, because once we get down to at most one stone, we're going to stop. So essentially what we would do is for I stone in stones, we'll have like our max index equal to 0 to start. We'll say if stone is greater than stones max index equals I. So we're going to update maxes, and we're going to have to actually do this twice. So then what we would do is we would say stones -1, stones max index. I have to shift over a little bit. Equals stones max index. This is how you swap numbers in Python. And then we would simply just assign, I guess, x to be stones.pop. And then, oh, sorry, this should be here. And then we're going to do this Same thing again, but for y. I know it's bad to copy paste code, but this isn't the solution that I'm really looking for if I'm an interviewer. So I'm going to try to keep this as short as possible. But now you check. Well, first let's sort these so we know that x is less than or equal to y, like they say. Now, if x equals y, then we're just going to continue. We've gotten rid of the stones. Otherwise, y minus equals x, and we can append y because we're creating a new stone of y minus x value. And then outside of this while loop, we're done with all the stones, so we can return stones 0 if stones, else 0 because they want us to return 0 if there are no stones remaining. Now if we run this, oh, whoops, I forgot to enumerate this here. So now let's try that again. Again, I forgot I copy paste. This is why you don't copy paste code, because it makes, if you have to change anything, you'll have to change it in multiple places. But okay, so the very two basic test cases pass. This is a fine solution considering we're only dealing with length 30 at most, but it is O of n squared because it's going to take, well, you could have to go through it n over 2 times because you're smashing 2 stones every time and then potentially creating a new one. So it's O of n times whatever is within that loop. Well, within this loop, we have to go through each of the stones and figure out what the maximum element is. So that's also going to be, that's an O of n thing. So n times n gives us O of n squared. We don't want to do this solution if we're in an interview. Obviously, it's fine to have this as your first solution. But when you're constantly having to get the maximum element, you might think you want to sort it, but you actually want to use something called a heap. So I'll use, I'll actually import what we need and not everything like I had before with the star. But essentially a heap is something where the first element within the heap will be your minimum element within the heap, and then everything, it's designed as like a tree where you have the minimum and then everything below it will now be less than, or I guess greater than the minimum element. And then in the right subtree, you have this node has some value x, and then everything below it will also have a value greater than or equal to x. So it has this nice property where the root of the tree is the absolute minimum. In this case, we want the maximum. Python implements it as a minimum heap. So we're going to have to do a little bit of finagling here where we get the negative or the negation of each stone, and then we can heapify this. And now instead of having to do this stuff where we find the maximum, there's a nice thing that we can do where we just do, actually we don't have to get rid of everything because this stuff should stay the same. We'll say x equals heap pop stones and y equals heap pop stones. Then we still want to sort those two. We want to just make it so that x is the smaller one. X equals y, continue. Now instead of this, we will heap push y. So essentially what we're doing is we're getting the maximum element, and then after you heap pop, the heap will now rearrange whatever it needs to so that the new maximum, or I guess, yeah, our new maximum is at the top. So we heap pop again. So we have the 2 maximum elements from our stones. We now check to see if they're equal. If they are, then we don't need to do anything else. We've already destroyed them. Otherwise, since they're not equal, we need to create a new stone of y minus x value. We now heap push that. So that just means put this in our heap, and if it needs, usually you put it at the bottom, and then if you need to, oh, sorry, I just realized this should be a negative y because we're doing a bunch of negation stuff here. And since we've negated everything here, we also need these two to be negative. But that should work now. But yeah, essentially the stone that we've created will now bubble to the top if it is the maximum element, or it'll rearrange itself so that it is within, or is where it needs to be to maintain the heap structure that we want. The complexity of this is now, well, we have n iterations here, or n over 2, and it doesn't really matter, O of n iterations. And then this heap pop, I'm not 100% sure. I know it's either log n or constant. It's at least at most log n, so I guess O of log n. And then this is constant because there's only two elements. This is constant quality check, and then this here is definitely O of log n. So we have n times log n. So our complexity of our algorithm is going to be O of n log n, which is as good as you can do because you are trying to get this max. Oh, sorry. Also have to return negative stone 0 if stone's else 0. But now we can see, well, you can't really see very well, but the test cases pass, and if we click submit, it all passes. So yeah, thank you so much for watching. Hopefully this wasn't too difficult to follow. I know if you are familiar with the heap data structure, it would be almost impossible to come up with this solution, but I will leave a reference down below, probably Wikipedia, because I find that that's usually the best resource in terms of explaining things concisely and clearly. At least I found that with some other things that I've linked in the description. But yeah, thanks so much for watching. Please like and subscribe, and I'll see you guys next time.